Assalamualaikum and have a very good day, Doctor. So, today our group will be representing on our topic of thermodynamics in refrigeration. So, let's take a look at the refrigeration system. This technology is something that we interact with daily, but it also plays a critical role in global industries. So, here are the team members, which is Shukri, Muaz, Liana, and Amira. So in these slides, first and foremost, what do we mean by refrigeration? At its core, it's simply the process of removing heat from a space or substances to lower its temperature. In other words, it's also about controlling heat to create cooler environments. The importance are it ensures food preservation and safety, keeping our meals fresh and preventing spoilage. It's vital in pharmaceuticals and medical storage, where vaccines and medicines must be kept at precise temperatures. It also provides comforts, cooling in homes and buildings. And beyond that, it's essential for industrial and manufacturing processes and chemical production to electronics. And lastly are the applications. Now, everyday examples include refrigerator in our kitchens, large-scale cooling facilities in industries, supermarket aisles filled with chilled products, medical storage rooms, safeguarding sensitive supplies, and air conditioning units that keep our spaces comfortable. These applications highlight how refrigeration touches nearly every aspect of our lives.
So in this slide, I will explain about the working principle in the vapor compression refrigeration system. So there are four main components, which is the compressor, condenser, expansion valve, and also evaporator. Basically, the working principle of this refrigeration cycle is the refrigerant will circulate through the components and absorbing heat from the low temperature region and rejecting heat to the high temperature region. So firstly, at the evaporator, the heat is absorbed from surroundings, thus it will cool the space. And then the compressor then adds work input to raise the pressure and temperature of the vapor. Next, condenser will reject the heat to the environment, and finally, the expansion valve will reduce the pressure before the refrigerant returns to the evaporator. So I will explain about the first key process, which is compression. So in the compression stage, the refrigerant is compressed by the compressor, so hence the name, the process name, and this will increase its pressure and also temperature. So as we see from a thermodynamic perspective, this process will require work input, which makes it endothermic. And the enthalpy of the refrigerant increases as it behaves approximately as an ideal gas. And this high pressure, high temperature vapor then flows to the condenser where heat is rejected to the surroundings.
So now we go to condensation process. Condensation is the phase where hot high pressure vapor from the compressor transforms back into a liquid state. During these transitions, the refrigerant rejects significant thermal energy into the surrounding ambient air or water. This isothermic process typically occurs at a nearly constant pressure within the condenser intricate coil network. The efficiency of this heat transfer is dictated by physical design choices like fin density and tube conductivity. Finally, the strategic use of fans help maintain consistent airflow, ensuring that the maximum amount of heat is dissipated effectively. Evaporation occurs as a low pressure liquid refrigerant absorbs thermal energy from its surrounding to reach a boiling point. As the fluid vaporizes, it effectively pulls heat from the cold space, creating the desired refrigeration effect. This phase change is an endothermic process that relies on maintaining a low pressure environment within the coils. Furthermore, the performance of the evaporator scales directly with its physical footprint and the total surface area available. Ultimately, optimal coil geometry and high airflow are essential component for maximizing the system overall heat absorption capacity.
Next, we go to the thermodynamic rule block. On the left, we can see the coefficient of performance (COP). Unlike engine where higher efficiency means producing more work, refrigeration efficiency measures how much cooling is produced for each unit for electrical energy use. For example, a COP of 3 means using 1 unit of electrical energy produce 3 units of cooling. Therefore, a higher COP indicates a more efficient refrigerant system. So next we go to the uh, defining the efficiency. The first principle is Carnot cycle, which is define the maximum possible efficiency of any refrigeration system. In reality, no system can achieve 100% efficiency because energy is always lost through friction, heat transfer, and other unavoidable processes. The second, we should determine the refrigerant choice. So, engineers choose refrigerant based on properties such as latent heat, operating pressure, safety, and environmental impact because it is very important to make the refrigeration system is very efficient. Then next we see the operating condition. Changing a vibration temperature requires a changing system pressure. So a delicate balance, starboard evaporation, or block condenser cause a system failure. So a good operating condition must be determined to increase the efficiency. Next, we go to the comparison within the system evolution. So the first one is the refrigerant chemistry. The oldest one we use high JWP synthetic, which is R134A and R410A, which is not good for the environment because it releases a green gas. The next generation system is we'll use a low GWP alternative R1234YF and R32 and a return to a natural refrigerant like CO2 R744 and ammonia R717, which is good for the environment because it releases low green gas. The next one is the compressor technology. The oldest one we use fixed speed, so we cannot adjust the speed. We just on the and off the cycle, which is consume a lot of energy. The next generation we use smart inverter compressor that dynamically vary speed to perfectly match real cooling demand. The next one is energy strategy. Passive thermodynamic loops reacting to real-time demand, which is the old one. So the latest one we use ejector cycle, recovering expansion energy, and the thermal storage synchronizing with the grid, which is very save energy and good.